Last section I mentioned that there were going to be some calculator commands that were going to be very useful when working with a binomial distribution. So that's what this section of notes is going to be all about. There are actually two different calculator commands that will do the binomial formula for you. So remember, binomial formula from the previous section was this formula right here, which we can use to find binomial probabilities and makes our life a little bit easier so that we don't have to think about it every single time. Well, today the calculator is going to make it even easier for you because you really don't have to do a whole lot. So the two different commands are binompdf and binomcdf. For binompdf, this is the probability that x is equal to k. So this is when you want to know what the probability of a certain number of successes is for your formula. Now, again, remember that n is equal to your number of trials in each of these, that p is your probability of success, and finally that k represents your number of successes. So for binompdf, all you have to do is type in binompdf, your n, p, and k, close your parentheses, and you're good to go. Now binomcdf is also useful. This is when you want to know what the probability is of getting a certain number of successes or less. So in other words, the probability that x is less than or equal to k. In order to find that, same idea, we have binomcdf, n, p, and k. Perfect. Now, this next part you can cross off. Obviously, we are not AP stats. We are just regular stats. They do get to use the different calculator commands on their exam, but that doesn't apply to us. So let's take a look at an example of how to use these. So in this example, in roulette, there are 18 out of the 38 spaces which are black. Suppose you observe the next 10 spins of the roulette wheel. So first off, notice that this is binary. So it does, if we're going through bins, which remember is what we're checking to make sure we can use binomial distribution, binary because you either get black or don't get black, independent because the trial before doesn't affect the next, n is 10 spins, so we're good there. And your probability of success is 18 out of 38, so we're good there. And so let's go ahead and write out what that means. We know that n is going to be 10, and we know that p is going to be the 18 out of 38 spaces, which are black. So for part A, what is the probability that exactly 4 of the spins land on black? So we want to know what is the probability that x is equal to 4. In other words, we're going to use 4 as our k value. So what we need to do on our calculator is type in binompdf. Our n is 10, p is 18 out of 38, and k is 4. And without even having to use the formula, the calculator is going to do it all for us. To get to binompdf, it is the same place as normal PDF and normal CDF. So if you hit second vars, you'll get there. Now binomial is towards the bottom of the list, so if you hit the up arrow, you'll get to it a little bit quicker, and we're choosing option A for binompdf. For our number of trials, in this case we have 10 trials. For our probability, p, that's 18 divided by 38. And for our x value, our number of successes, that would be 4. So when we put all those in, we'll hit paste. Obviously, if you don't have the menu like I just had, you'll have to remember the order in p then k, separate with commas, press enter, and we'll get that probability is 0.2247. So you can see how easy that is. To just show you that it works, let's go back and think about maybe rolling 2 6s, or what is the probability of rolling 1 6 in 4 dice rolls? And we found that to be 0.3858, and you remember all that work we had to do that. Well, now what we're saying is the probability that you get 1 6, that x is equal to 1, is that we could have just put this into our calculator as binompdf, where n would have been the 4 rolls. Our probability of getting a 6 is 1 out of 6, and we want exactly one of them to be a 6. And if we put that into our calculator, so second vars up to binompdf. Oops, we went too far. So binompdf, our n value was now 4, so 4 trials. P is now 1 out of 6 for our probability of success, and we wanted one of those to be a success. Hit paste or put that into there, and what do you know? 0.3858, a heck of a lot easier than what we would have done in the previous video. But it's a good idea to understand where that comes from and not just to know how to put it in your calculator. Let's next take a look at a probability where you want to know not just one, but multiple successes. So what is the probability that at least 8 of the spans land on black? So in other words, what is the probability that x is greater than or equal to 8? Well, I suppose you could do that by taking the probability that x was 8 plus the probability that it was 9 plus the probability that it was 10, but now you're going to have to find 3 probabilities when you could just find 1. Now here's where you do have to be a little bit careful, and we're actually going to use one of the rules that we discussed in a previous unit to get this. But binomcdf works when x is less than or equal to k, just not when it's greater than or equal to. So if we want to know what it's probably that it's greater than or equal to 8, let's just take 1 minus the probability that it's less than 8. Well, if it's less than 8, that would be the same as finding the probability that x is less than or equal to 7, since 7 is the next lowest number from 8. So either we have 8 or more successes, or we have 7 or less successes. Which, now that we've got it written this way, we can just use binomcdf to find that. So binomcdf, where n is still going to be 10, p is still going to be 18 out of 38, and k this time is now 7. So let's go ahead and put that into our calculator. Don't forget the 1 minus before you find binomcdf. And then once we've got binomcdf, we're going to put in that n is 10 still. Our probability of success is 18 out of 38. And our x value in this case is 7. And that'll tell us that that probability is 0.0385 to 4 decimals. All right, so we also haven't talked much about the mean and standard deviation of our binomial distribution, so let's go ahead and talk about that now. So in this example, let's let x be the number of the next 10 spins of the roulette wheel that land on black. And we want to calculate both the mean and standard deviation. Just a reminder, again, that n is those 10 spins, and that p is 18 out of 38. So to find the mean, it tells us that we're going to take n, which is 10, multiplied by p, which is 18 out of 38. So if we take that 10 multiplied by 18 out of 38, we're going to get that that is equal to 4.74. So to interpret that, we would say that in 10 spins, we would expect about 4.74 to land on black. So a little bit less than half of the spins we would expect to land on black, which should kind of make sense because our probability of getting a black would be a little bit less than half. 18 out of 38 is a little bit less than 50%. For standard deviation, we'll go ahead and calculate that now. So we're going to take n times p times 1 minus p, so that would be 10 multiplied by 18 out of 38 multiplied by 1 minus 18 out of 38. Which, if you think about it, this first part, the NP of standard deviation is your mean. So when you're calculating standard deviation, just take the answer that you just got, multiply it by 1 minus p, so 1 minus 18 out of 38. And then once you've got that, just take the square root of it, and that will give you your standard deviation, which in this case is 1.58. So on average, you would expect for the number of times that it lands on black to be off from the mean by about 1.58. So how often then will the number of spins that land on black be within one standard deviation of the mean? That actually just goes back to the empirical rule from Unit 3. Empirical rule says that 68% are within one standard deviation, and that's going to be the case here as well. All right, so for this last part, when is it okay to use the binomial distribution when you're sampling without replacement? To illustrate what that means, let's say you are drawing cards and you want to draw looking for clubs. Then after you've drawn when you draw the first card, there are 13 clubs out of the 52. But then the second time, if you don't put the card back and you didn't get clubs, now there's 13 out of the 51 cards. And then 13 out of the 50 cards. And then 13 out of the 49. And the problem is the probability of success is not the same each time. So it's going to be hard to use binomial because that doesn't meet the last part, which is the S. The probability of success has to be the same. So that's why this is an issue, is that your probability of success must be the same. And when you're sampling without replacement, it's not the same. But when is it okay? It's okay as long as your capital N, so your sample space, is much larger than your sample. So when capital N is much larger than lowercase n. So let's take a look at an example of where this is the case and see that we are still able to use the binomial distribution for it. So for this example, there's a certain cereal company that put 5 different cards into each box of cereal. Each card featured a driver: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. And suppose that the company printed out 20,000 of each card. So in total, there were 100,000 total boxes of cereal with a card inside. So if a person bought 6 boxes at random, what is the probability of getting 2 Danica Patrick cards? Now, obviously, in this case, we are sampling without replacement. It's not as if we're going to look at one box and then put it back. And so that's going to be an issue, but keep in mind there's 100,000 total boxes of cereal, which would be our capital N, and we're only looking at 6 boxes. And so 6 boxes would be our lowercase n. And 100,000 is much bigger than 6, so we're going to be okay. So we're going to go ahead and use our binomial distribution to solve this. So what we want to find is what is the probability that they get 2 Danica Patrick cards in 6 boxes. Well, let's first think about what is the probability that they get a Danica Patrick card. That's going to be the probability that they get 1 out of the 5 different drivers. So there are 5 different drivers, so our probability of success is 1 out of 5. Now there are 5 different cards in each box, so there's going to be 30 different cards that we're going to be looking at. So n is going to be equal to 30. And we want to know what is the probability that we get 2 Danica Patrick cards, so that's going to be that x is equal to 2. So in order to find that, since it's equals, we're just going to use binompdf. Only use CDF if it's less than or equal to or greater than or equal to. For n, we've got 30 cards that we are going to have. We've got a 1 out of 5 chance that one of them is a Danica Patrick card. We want to know what is the probability that we get 2 Danica Patrick cards exactly. So we're going to go into our distributions menu, choose binompdf, and then once we've done that, we're going to go ahead and type in everything we need. So our number of trials in this case was 30, p was 1 out of 5, and our x value or k value is 2. And so our probability that we get 2 Danica Patrick cards is going to be 0.0337. Now remember that this is getting exactly 2. It's not saying the probability that we get at least 2 Danica Patrick cards, which might actually be a greater probability. In fact, it should be a greater probability. Because if you think about it, out of those 30 cards, what our expected value is, if we take 30 and multiply by 1 out of 5, that's going to be 6. So we expect to find 6 Danica Patrick cards. But obviously, with our probability of exactly 2 being less than 6, it's going to be a much smaller probability. All right, guys, that wraps up our unit number 5. That does it for our discrete random variables, and in particular, this last one, our binomial random variables. Until next time, have a great rest of your day.